Welcome back, everyone. We are in Concept Development Practice page 6.1, which is on friction. And friction, remember, is any force that's opposing motion, and it's caused by the microscopic or even less than microscopic roughness of two surfaces that are dragged or moving across each other. So they don't want to go. They're blocking each other's path, and so some things are very smooth, and other things are not so smooth. And so you can find out, based upon measuring two things moving across, exactly what the friction is. So here's some examples. A crate filled with delicious junk food rests on a horizontal floor. Only gravity and the support force of the floor act on it, as shown by the vectors for W and N. So its weight, remember, is mg. That's the mass times gravity. And N is exactly the same force that weight is pushing down, the floor is pushing back up on, so that it doesn't fall through the floor. The net force is what? 0 or greater than 0? Okay, well, if the net force is exactly the same as the weight coming up, and they're opposite directions, they cancel each other out, so they have a net force of 0. And why do you know that? Okay, what does force do to a mass? Okay, if you have a force, a net force acting on a mass, it will accelerate that mass. And so since this is resting on the floor, we know that it's not, that there isn't a net force because it doesn't accelerate. So no acceleration. All right, number 2, a slight P is, I guess that's pull. So it's a force acting in the forward direction is exerted on the crate, not enough to move it. A lot of people will miss this, so be careful to understand if you can. If you push on something like a wall that can't move, or shove on a refrigerator and it doesn't budge, or pull on something and you just can't make it move, you haven't really done anything to it. The force that you've exerted is a force, it'll make you sweat, but it's not enough force to move something if the friction force is higher than your movement force. So the stickiness between the two surfaces is big enough, it'll keep you from pulling something. Conversely, if you have something that's slick enough, even if it's heavy, you can move it with a light force, depending upon how slick the two surfaces are. So it says the force of friction F acting on the crate is equal to, less than, or greater than P. Okay, so we need to know it's not enough to move the crate. What do you think? Okay, well, if you remember, this P is formed by forming a perpendicular, or a parallelogram with the normal force and the weight. So the force is going to be the same in the back direction because essentially you've got the same angles working in the front as you do in the back. So if you pull a force here, the friction is going to be equal to that pull, which means you pull harder, it's possible that the friction force could be equal to that pull. Eventually you're going to move enough that's going to overcome static friction, it'll start moving. Once it's moving, you only need to pull it equal to its force, or equal to its friction force, in order to move it. But it might take a lot to get it started. Like once it's started, it's not so bad. So this is actually going to be equal to. The friction force is counterbalancing this, because otherwise, if this didn't, you would be moving it. Think about it. If you put a force here that's not exactly the same in the back, it would be moving. So these two are going to be equal to, and there's still enough stickiness to the floor that it's not overcoming. Once it were moving, this would be all the force you would need to pull it. Is exactly the opposite of friction. Okay, so number 3. Pull P is increased until the crate begins to move. It's pulled so that it moves across the floor with constant velocity. Okay, now this is just what I was saying. Once it's moving, I only need pull P to be the same as the friction to keep it going at a constant speed. So let's see, it's moving at a constant speed, so friction is equal to, greater than P. It's equal to. So what you're going to see is that getting something to started The mu that's called static, okay, static is very high, okay, something like this, and then the mu of sliding, okay, sliding friction is much lower. Okay, so to get something going is high, and then get something keep on sliding once it's sliding is not so bad. Okay, B says constant velocity means acceleration is 0, constant. It's not getting faster, it's not getting slower. So remember, this is just inertia. An object in motion tends to stay at motion with this force unless acted upon by another force. So as long as these two forces are equal, if it's stopped, it stays stopped. If it is going, it stays going. That's kind of pretty cool. The net force on the crate is, so this is C, equal to 0? Yes. Okay. If you're not accelerating, then you do not have a force acting upon a mass. Okay. So if it's not accelerating and it's going at a constant speed or stopped, both of those, you're going to have a force equal to 0. I would say more than 75% of students have trouble with this concept. They don't quite get it. Ask yourself, do you understand? And ask me a question in class if this is something that you're like, I'm not sure I understand. How can this be equal to 0 if I'm moving it and I'm pulling a force on it? But you're seeing these forces are equal to each other, and as long as it's moving, you can keep it moving with this force. It's not enough to start it moving, okay, because this force is opposed to it. But once it's moving, that I can keep these two forces equal to each other. Okay, number 4. Pull P is further increased and is now greater than friction. All right, so this is greater than friction. Friction is pulling back, but not as much as you're pulling forward. The net force is, okay, if this force is greater than friction, then I have a net force. It's greater than 0. And you knew what the next question was. If it's greater than 0, is it accelerating? Yes, okay, because F equals ma, and if you put a net force on a mass, you will accelerate that mass. So the net force acts to the right, so acceleration acts to the. Is it getting faster in what direction? You're getting faster in the direction of the bigger force, so it'll be to the right. Okay. Number 5. If the pulling force P is 150 Newton and the crate doesn't move, what's the magnitude of F? Okay. So if you pull on P and it's stuck, then friction is going to be equal to 150 newtons. Okay, it's not enough to keep it going. If the pulling force P is 200 newtons and the crate doesn't move, well then it's, not only you are a wimp, but your stronger friend is a wimp. It's still not enough to push that refrigerator or whatever you're moving. If the force of sliding friction is 250, what Newton force is necessary to keep the crate sliding at a constant velocity? I'll pause for effect. I hope you can answer this question. Once it's already moving, how much force do you need to keep it moving? Once it's moving. If it's moving, you only need to overcome friction. So if friction is 250 to the left, then you're going to need 250 newtons to the right to keep it sliding, if it's already sliding. And the last question, if the mass of the crate is 50 kilograms and sliding friction is 250, what is the acceleration of the crate when the pulling force is 250? Okay, so let's look. Mass is 50, so we need to know how much that is, because remember, do we know sliding friction? Okay, sliding friction is the amount going backwards. Okay, so what's the acceleration of the crate if the pulling force is 250? Well, if friction is 250, okay, and you have a force of 50 kilometers down, and it's stopped. I assume this is stopped. Do I assume it's stopped? It doesn't say. I'm sorry. I'm getting a little confused. If it's sliding, the sliding friction is 250 newtons, so that's just in the back. What is the acceleration of, if you're putting 250 to the front? it's moving at a constant speed. If this is moving, because I get that by this is a sliding friction, it's sliding, then I only need the same to keep it going. So if I've got the same, I have got 0 meters per second squared. It's not accelerating. I'm going at a constant speed. Okay. So what about the next one? 300 newtons. So I've got 250 backwards. I have 300 newtons forwards. That means I have 50 forwards. Okay, 50 newtons forwards, and it's 50 kilograms. So it's 50 kilograms. So 1 newton moves 1 kilogram 1 meter squared. So how many does 50 newtons work on 50? If 1 newton pushes 1 kilogram 1 meter per second squared, can accelerate at 1 meter per second squared, then 50 can accelerate 50 1 meter per second squared. Okay. And then what about 500 newtons? So I've got 250 back, I've got 500 forward. That means I have 250 forward. Okay, 250 or 50 into 250, because I've 250 newtons, but I got 50 kilograms. So each of those kilograms have to be 1 newton has to be working on 1 kilogram. So that means I'm going to divide 50 into 500, and I'm going to get 5 meters per second square. Okay, I think I ruined number 8 for you, and nobody could probably understand what I just did. But I hope you're getting closer and closer to perfect understanding. I'll see you in class.